Good afternoon. Just again looking into the problems we have been dealing with in the case of exponents and logarithms, as well as systems of equations. And let's see, and we had left off, with logarithmic equations. And if we look in the case of number 11, so we have in this particular setup case, so we have -6 times the base 4 logarithm of 5x is equal to -12. And for what we have in this one, so we have in 11 case, they have -6. There we go. So they have -6 times the base 4 logarithm of 5x is equal to -12. And for what we have here, it's kind of like one of the problems we had from the first review handout. Instead of trying to do anything fancy with the -6 and make it into an exponent, what you can do is divide the whole equation by that coefficient and simplify that particular equation. So if I divide both sides of the equation by -6, we're going to have the problem to become somewhat simplified, whereby we're going to have now the base 4 logarithm of 5x is equal to 2. And just reminder, for whatever we have for 5x, 5x must be positive. So now we got the base 4 logarithm of 5x is equal to 2, and just looking at taking care of the base 4 logarithmic appearance. So I can take the property again where we have a to the base a logarithm of x is equal to x. So I can make the left hand side of the equation at 5x. So I can take care of the base logarithm of 4, treating both sides as powers, to which the exponential base 4 will be raised. Alright, so I have 4 to the base 4 logarithm of 5x is equal to 4 squared. And so the left hand side, this will become 5x, and 4 squared is equal to 16. And we have with division by 5, it's going to turn out that for x you can either express as a fraction or as a decimal. And so we have for this final result, we have x is equal to 16/5. And again, as a decimal, you can write as 3.2. And you can go back and check 5 times 16/5 or 5 times 3.2. That will be at 16, and 5x hereby is positive. All right. So number 11 does have one solution. Now, for what we have in the case of number 12, so now we have working with natural logarithmic term, and here we have the sum of 4 plus the natural logarithm of the quantity of x minus 5 is equal to 3. And it says here to round your answer to the nearest hundredth. And so for what we have here in 12, so we have 4 plus the natural logarithm, and that's the quantity of x minus 5, is equal to 3. And so we have with the logarithmic term, the attachment is at x minus 5. Okay, so whatever we have for x must ensure that x minus 5 be positive. Okay, and starting things off, okay, so I can isolate the natural logarithmic term. Okay, so I can take 4 and subtract from both sides. Okay, so I have the natural logarithm of x minus 5 is equal to negative 1. Okay, and again, so for natural logarithm, okay, again, natural logarithm is going to be a base e logarithm. And you don't have to write out in terms of base e, but again, okay, we're going to take care of the natural logarithm again by applying again the property that a to the base a logarithm of x is equal to x. Okay, so your a is going to be at e. So you have e to the base e logarithm, or natural logarithm, of x minus 5 is equal to e to the negative 1. And so we have left hand side is going to become x minus 5. And for what we have in the case of e to the negative 1, okay, and for this number, okay, we have a decimal here, so among the first digits, okay, we have like 0.3678. And looking at solving for x, so if I add 5 to both ends, okay, so we're going to have x. We have among the first digits, okay, so we have 5.3678. And again, the problem is asking, okay, to round to the nearest hundredth. Okay. And so for what we have here with 5.3678, okay, so we have to the nearest hundredth, or to the nearest 2 decimal places. Okay, so we want to have the x is going to be equal to about 5 point, okay, and 100 places with 6, and next to 6 is 7, so the 7 in the thousandths place, since that digit is 5 or greater, is going to signal that 6 is going to round up. And so in this case, we have that x is equal to 5.37 when rounded to the nearest hundredth. Okay. Now, in the case of our other problems regarding logarithms, and here we have for number 13, okay, we have the base 10 logarithm of the quantity of x plus 5 minus the base 10 logarithm of 6 is equal to the base 10 logarithm of x. And for what we have in this problem, so we have for number 13, okay, so we have the base 10 logarithm, okay, we have of the quantity of x plus 5, we have minus, okay, the base 10 logarithm of 6. Is equal to the base 10 logarithm of x. Okay, and again, whatever we have for x must ensure that both x and x plus 5 be positive. And again, the attachments cannot be 0 or negative. Okay. And so, looking at what we have now, okay, so you have the base 10 logarithm of x plus 5 minus the base 10 logarithm of 6 is equal to the base 10 logarithm of x. Now, for what I have in the case of the difference of these logarithmic terms, I can consolidate as one statement. And again, so looking at condensing or combining as a single logarithm. Okay, now again, subtraction is going to imply division between the attachments. Okay, so we have on the left, okay, we have base 10 logarithm. Okay, so you have that of x plus 5 minus that of 6. Okay, and with x plus 5 as part of a positive base 10 logarithm, we're going to have that in the numerator, and since 6 comes from a negative, this will be in the denominator. Okay, and so we have now base 10 log of x plus 5 over 6 is equal to the base 10 logarithm of x. Now we got the same base on both sides, and that means that we can set these attachments equal to each other. Okay, so we can go ahead and set x plus 5 over 6 equal to x. And what I can do here, okay, is I can multiply both sides of the equation by 6. So as to get out of the fraction mode, so we have x plus 5 is equal to 6x. So I have 6x by itself on the right, and I can join this with x. So if I take x away from both sides, okay, so we're going to have that 5 is equal to 5x. And we have with division by 5. Okay, so I have that 1 is equal to x. Okay, so we have the x is equal to 1, and just checking, so 1 plus 5 is 6, that is positive, and x at 1 is positive, so this value does check out upon inspection. Okay, so 1 is going to be the solution for what we have in number 13. Alright, now in the case of what we have for number 14, okay, and this time, okay, we have an exponential equation that is going to share a common base, and you can treat what we have in 14 as an equation that has a common base, or it could be treated as if there were no common base. So you can apply either brand of treatment. Okay, and now, so we have in 14, so you have 64 is equal to 32 raised to the x minus 4 power and so we have here, okay, so for 64 equal to 32 to the x minus 4 degree. Okay, and we can treat this as a problem, okay, that shares a common exponential base, and that number that will multiply itself into both 64 and 32, okay, that is going to be at 2. And so if I take that approach, the common base approach, now we have a 64 is going to be, it's going to have like 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, and then have times 2 is 64. So it would take 6 2's to multiply out to 64. And for 32, we have 2 to the 5th and 32 to the x minus 4. Okay, in terms of base 2, you have 2 to the 5th raised to the x minus 4. And again, on the left, okay, so I have 2 to the 6th. Now to the right, I can remove the parentheses, whereupon have 2 to the 5 times all of x minus 4. And we have with the power property of exponents. Okay, so multiplying the powers. So we'll have 2 raised to the 5x minus 20. And looking at what we have now, Okay, so we have single base 2 terms, and in that setting I can go ahead and set the degrees equal to each other. So here we have 6 is equal to 5x minus 20. And just isolating the 5x. So if I add 20, okay, so we're going to have that 26 is equal to 5x. And we have with division by 5. Okay, so it's going to follow that 26 fifths is equal to x. So for x, you can either write as a fraction or as a decimal. Okay, so you have x is equal to 26 fifths, and writing as a decimal, let me say that x is equal to 5.2. Now just mention, okay, if the common base approach did not immediately come across as the approach to take, you can still kind of go through a change of base route. Okay, so you have like 64 is equal to 32 to the x minus 4, and you might think, okay, maybe not in terms of where there's a common base, but where you know that the logarithmic base 64 and 32 are not in a typical scientific calculator, and for those routes you could take natural or base 10 logarithms, and we'll take the base 10 log for these. So if I have a base 10 logarithm of 64 and set equal to the base 10 logarithm of 32 to the x minus 4, okay, so I have the base 10 logarithm of 64, and for what I have on the right, now we got 32 to the x minus 4, and for what we have here, I can write x minus 4 as a binomial coefficient. Okay, so I have the base 10 log of 64 is equal to, and if I distribute, okay, so we have x times the base 10 logarithm of 32 minus 4 times, okay, the base 10 log of 32, so I have one x term, and that's going to be x times the base 10 log of 32 and just isolating what I have in x so far. Okay, so I'll just add. Okay, so we're going to have the base 10 log of 64 plus 4 times, okay, the base 10 log of 32 is equal to x times, okay, the base 10 log of 32, and So we have with division by x. Okay, so I have x equal to this ratio, and so we got here. So we have, again, the base 10 logarithm of 64 plus 4 times the base 10 logarithm of 32 over the base 10 logarithm of 32. And just putting into calculator notation. Okay. So I have in this item, okay, so I can say I have the base 10 logarithm of 64 plus 4 times, okay, the base 10 logarithm of 32 so close out for 32 and close out for the sum. And we have divided by the base 10 logarithm of 32. Okay, and so for what we're going to have in this case, all right, so you can have the base 10 logarithm of 64 plus 4 times the base 10 logarithm of 32 divided by the base 10 logarithm of 32, and that would come out to 5.2 as well. All right, so just looking at what we have in the result. So if you got the common base, chances are you will have worked through the problem more quickly. Okay, but again, if you were to take like just treating as what we have for equations, okay, that might have no common base. Okay, you can take base 10 or natural logarithms on both sides. Okay, so and there are other pathways too. In fact, I can think of another one, but just to kind of show you, there are various ways or pathways that you can go about solving for exponential equations, and this is such a case. Now, for what we have in the case of number 15, okay, so we have a situation, okay, about like what we had earlier, okay, with number 12, and we have in the case of number 15, and it says here to solve for x in the equation below, and again we're involving natural logarithms, where here we have an exponential equation with the natural logarithm of exponential base e, and we have this raised to the x minus 4, and this is equal to 4, and it says to round your answer to the nearest hundredth. Okay, so we have for number 15, okay, so you have e to the x minus 4 is equal to 4, and again, okay, just kind of shifting gears, you're going to have like a base a logarithm of a to the x is equal to x, and for what we have in the case of this problem, okay, so I can go from e to the x minus 4 to just x minus 4. If I take the natural log of both sides, we either say that we have ln or base c logarithm of e to the x minus 4, and so the left hand side, okay, we have an x minus 4 and base c logarithm of 4, okay, that is going to be the natural logarithm of 4, and as a decimal, now we have the natural logarithm of 4, okay, you have among the digits, you have 1.38629, and adding 4 to both sides. Okay, so we're going to have here okay, so you have x equal to 5.38629. Again, to the nearest hundredth. And we're going to have for x itself. Okay, so you got 5 point, okay, and then we have 8 in the hundredths place and the 6 alongside it, with 6 being 5 or greater. Okay, this signals that the 8 is going to go up, and to the nearest hundredth. Okay, so we have for x, this is going to end up at 5.39. All right, now for what we have in the case of equation systems, now we have N16. Now we have linear equations, and whereupon we have for the first equation, okay, so we have 4x plus 2y is equal to negative 8. And for the second equation, now we have 3x minus 2y is equal to 29. And for what we have in this system, okay, so we have additive inverses already with positive and negative 2y. So if you look at elimination by using the addition method, okay, so we have here, we got 2y and negative 2y. So these will go out, and we have 4x plus 3x, 7x. And we have negative 8 plus 29. Okay, so this will be a positive 21. So we got 7x is equal to 21. And we have with division by 7. So it's going to follow that x is equal to 3. Okay, so we have half the solution with x at 3. And then I can plug in 3 for x into either of these two equations, and I'll just take x into x for the first equation. And so just looking at what we have here, so you got 4 times x plus 2y is equal to negative 8. And again, just plugging in 3 for x. Okay, so you got 4 times 3. Okay, so we have 4 times 3 plus 2 times y is equal to negative 8. So we have 12 plus 2y is equal to negative 8. And taking 12 away from both sides, so we're going to have that 2y is equal to negative 20, and with division by 2, okay, so it's going to follow that y is equal to negative 10. Okay. I'll just create a little bit of space here. Okay, so you have y comes out to negative 10. Okay, so we have in the case of the solution, so we have that x is equal to 3, and we have that y is equal to negative 10. And again, just in ordered pair terms, so we have x and y is equal to 3 and negative 10. And you can check your results here Okay, so you have like 4 times 3 is 12, 2 times negative 10 is negative 20, 12 minus 20 is equal to negative 8, and 3 times 3 is 9, and negative 2 times negative 10 is a positive 20, and 9 plus 20 is equal to 29. Okay, now for what we have in the case of the next item, and it's going to follow that 17 comes from section 8.2, and that's not even going to be in the ALEKS or your last exam, so a 3 equation system, don't worry about. But now in the case of nonlinear equation systems, and we have for the 18th and last problem, now we got y is equal to x squared minus 8x plus 2 Okay, so we have y as a quadratic function, and we also have it as a linear function. And just looking at what we have for number 18, so looking for those values of x and y that will belong to both equations in the system. And the results might surprise you a little bit. Okay, so we got for this system, and there was one case where we had like a switch around of the answers in x and y, like we had x equal to 6, y equal to 8, and vice versa. Now, for what we have in the case of this system, now we have y isolated, where in the first case we have it set equal to x squared minus 8x plus 2. Now, so we have it such that it is equal to negative 2x plus 18, and any variable that is isolated, okay, we can substitute for in the other equation. Okay, so you have from the first, I have x squared minus 8x plus 2 to represent y. And here, so I can substitute for y this expression, and solve for x. And so for what we're going to have in the follow through, okay, so we have x squared minus 8x plus 2 is equal to negative 2x plus 18. Okay, so I have a quadratic equation, okay, and it is not yet in standard form. So if I set the equation to 0, so I have the highest order term at x squared, which is on the left, and I can just move the 2x as well as the 18 by adding 2x and subtracting 18. And so we're going to have x squared minus 6x minus 16 is equal to 0. And looking at factoring, so with x squared, this will go to x and x. Factors of negative 16 with minus 6 sum or difference. This will signal that more weight will be given to the subtracting than to the adding. Okay, so we got x minus 8 is equal to 0, as well as x plus 2 is equal to 0. And looking at solving for x, okay, we have for x minus 8 equal to 0, we have that x is equal to 8. And for x plus 2 equal to 0, so we have that x is equal to negative 2. Okay, now we'll be looking at solving for y. And just, again, like sort of like what we had encountered the other day, where we had a linear as well as a nonlinear equation. Okay, if I have half the solution and I'm looking at plugging in and the equations are not of simpler degree, again, you want to plug into the simpler equation, simpler as in lower degree. Simpler or simplest equation. So between the two, okay, the simpler equation is going to be the linear equation. So we've got with y is equal to negative 2x plus 18. So if we're looking at plugging in, so plug into 8 for x, and also plug in negative 2 for x. So whenever x is at 8, so we have negative 2 times 8 plus 18. We have that y is equal to negative 16 plus 18. And negative 16 plus 18, this will come out to a positive 2. Okay, so one apparent solution, okay, we have with the point where x is at 8 and y is going to be at 2. Okay, so just again, taking what we have at the moment and just looking at the consistency. So for 8, 2, I can check. Okay, so if x is 8, 8 squared is 64. Negative 8 times 8 is negative 64. 64 minus 64 plus 2 is equal to 2. So the 64 and negative 64 cancel, plus 2, so you have y at 2. And negative 2 times 8 is negative 16. Negative 16 plus 18 is at 2. So the 8 and the 2 for x and y will check out. Now, for what I have with x at negative 2, we have negative 2 times negative 2 plus 18, and negative 2 times negative 2 is going to be a positive 4, and 4 plus 18 is going to come out to 22. Okay. And so we have another apparent solution set with negative 2 and 22. So we have for x at negative 2, and see if it balances out to 22 in both of these. So we got negative 2 times negative 2 is 4, 4 plus 18 is 22. And with negative 2 squared is 4. Negative 8 times negative 2 is positive 16. So we will have 4 plus 16 is 20, plus 2 is 22, and that checks out again for y. So for your solution, okay, we're going to have two ordered pairs. Okay, so we have xy, again at 8, 2 is one combination, and also xy at negative 2 and 22 as the other. Okay, and just kind of taking what we have, going back to exponents and logarithms. And we'll say that we have in the case of solving for x, Okay, tell you what. Let's see what we get in the case of let's say we have 4 to the x minus 3. Right, so let's say we have 4 to the x plus 3 is equal to 8 to the x minus 2. Also, we'll have, see, we have a logarithmic equation. We're going to say we have that the base 9 logarithm of x minus 2 is equal to 2 and just sort of shifting gears. Let's see what we get for x, say to about, well, in this one, okay, we say we have 9 to the x minus 2 is equal to 2. So here, last two, you have a lot of the same terms. The difference being that you have a base 9 logarithm, and in 3 you have a base 9 in the exponential capacity. So for the next few moments, let's see what we get for x among these 3 problems. Okay, tell you what, if we go ahead and look into these items, if you're still working on them, that's fine. And we have for the first item, okay, so we have looking at solving for x, and here we have the variable, okay, is on both sides of the equation, and this is one where we have a common base with 2. And again, if you were to treat this as if it did not have a common base and you did the base 10 or the natural logarithm on both sides, you could do that. It would just be a longer process in terms of arriving at the result. Now, for 4 and 8, okay, both of those numbers are both multiples and integer powers of 2. And for 4 raised to the x plus 3 power, okay, so 4 is going to be 2 squared, and 2 squared, in turn we have raised to the x plus 3. And for 8 to the x minus 2, okay, so 8 is 2 cubed, and we have 8 to the x minus 2 becomes 2 cubed to the x minus 2 degree. And now looking at applying the power property of exponents, okay, so we have on the left, okay, so you have 2 squared to the x plus 3, and so we'll be looking at multiplying the exponents. So we have 2 times, okay, the quantity of x plus 3, and to the right, and we have 2 times 3 times the quantity of x minus 2. So for what we have on the left, okay, so we have 2 raised to the 2x plus 6, and to the right, and we have 2 raised to the 3x minus 6 power. Now we have single exponential base 2 terms, and I can set the powers equal to each other. So we have 2x plus 6 is equal to 3x minus 6. And with the power set equal to each other, I can just move the x terms. So I'm going to just take 2x away from both sides and have the x term on the right. And I'm going to add 6 to both sides. Okay, and normally I would like to have the x term on the left, but since the higher one was on the right, I can sort of sidestep from having to work with negatives any more than is necessary. So here we have 6 plus 6 is 12, 3x minus 2x is x. So we've got 12 is equal to x. So we have the solution in x is going to be 12. Now, for what we have in the case of the second item, okay, so we have the base 9 logarithm of the quantity of x minus 2 is equal to 2. Okay, so we have a logarithmic equation, and again, we had the logarithmic term to exist on one side of the equation, and again, I can take care of logarithmic bases by applying the matching exponential base. Okay, so I have again the property a to the base a log of x is equal to x. So I got the base a at 9, and so I can treat both sides of the equation as powers to which 9 will be raised. So I have 9 to the base 9 log of x minus 2 is equal to 9 raised to the second. So the left hand side, then we have x minus 2, and have x minus 2 is equal to 9 squared, which will be 81. And if x minus 2 is 81, okay, so we're going to have the x is equal to 83. Okay, and just double checking, and again, so x minus 2 must be positive. So whatever the attachment is must be positive. Okay, and so with 83 minus 2 is 81. That is positive. So 83 checks out. And if you were to look furthermore, okay, 83 minus 2 is 81. And the base 9 log of 81 would be the base 9 log of 9 to the second, which would be equal to 2. So 83 is the value for x. Now, for what we have in the case of number 3, okay, so we have 9 to the x minus 2 is equal to 2. Okay, so 9 before was in logarithmic base position. Now 9 we have an exponential base in the setup. And now, so just shifting gears. Okay, so going from undoing logarithmic bases to undoing exponential bases. So now I'm going to have the base a logarithm of a to the x is equal to x. So just taking what we have here, okay, so once again we're taking the base 9 logarithm this time. So the base 9 log of 9 to the x minus 2 is equal to the base 9 logarithm of 2. So for what we have on the left hand side, base 9 log of 9 to the x minus 2, this will go to x minus 2. Again, we have is equal to the base 9 logarithm of 2. And in approximating the base 9 logarithm of 2, again, we can apply the change of base formula. Okay, so again, just a little reminder. We have like the base a logarithm of m. We say it's the natural logarithm of m over that of a, or with the same attachments, we can apply base 10 logarithms. Either way. And so we have a at 9 and m at 2. So I would say we have natural logarithms where m is going to be at 2 and a is going to be at 9. And for the natural logarithm of 2 over the natural logarithm of 9, okay, so we have x minus 2 at about 0.31546, and looking at adding 2 to both sides. Okay, so it's going to follow that for x, say if I round to about the nearest 4 decimal places. So if I add 2, so you have x is going to be about 2.3155. Okay, and just there's going to be a little bit of discrepancy in terms of the values, but in a sense you can go back and check this result. And what I mean by this case, if I have like 9 to the 2.3155 minus 2 is equal to 2. And if you were to take 9 and raise to the 0.3155, okay, so you would have like 2.0001, and again that is about equal to 2. And again the difference comes from just having rounded to the nearest 3, or in this case 4 decimal places. Okay, so that would be your answer if you took it to 4 decimal places. All right, and just a couple of quick items. Okay, now this part I said we will be looking into this, and it'll be an Alex, but it will not be in your final exam. And this is going to be just with this bit that's going to be regarded as partial fraction decomposition. And this is where you have a fraction with the denominator that can be factored, and where the factors will be denominators of individual factors. It'll be kind of like taking a whole and breaking it up in terms of like the sums and differences of the parts. And I'll just give you a case here. Let's say that if I were to write if I were to express in terms of partial fractions, like the sums and differences of partial fractions, and we'll say we have as a first case. Let's say we have 6 all over x squared plus 4x plus 3. Okay, now for what we have in the denominator, okay, is factorable trinomial. Okay, so we have x squared plus 4x plus 3 and just looking at what we have now. Okay, so we have 6 all over the product of x plus 3 and x plus 1. So x plus 3 is its own denominator factor, x plus 1 likewise. And let's say if I break this up, in other words, split up the x plus 3 and the x plus 1 as being their own denominators. Okay, so you have, so we can look at finding out just what fractions would be added together if we had the first fraction, say, with x plus 3 in the denominator, and the second one with x plus 1. Okay, so just splitting up what we have here, and say that if I multiply this part by the least common denominator. Okay, so you're going to have x plus 3 times x plus 1. And doing likewise, okay, throughout. Okay. So for what we're going to have on the left, okay, we have both x plus 3 and x plus 1 will go out. So the left-hand side of the equation, okay, we have as 6. Now to the right, okay, notice you have a was over x plus 3. So we'll have x plus 3's will cancel. But you have the x plus 1 factor to remain. So we'll have the distribution of a times x plus 1. Now for what we have in the case of b, okay, there's a bit of a role reversal. It's now x plus 1 that cancels, and the binomial x plus 3 that will be distributed over. And so just looking at what we have in the setup. Okay, so we got this equation, and we're looking at solving for a and b. So you have a over x plus 3 plus b over x plus 1. Okay, now we have two unknowns with a and b, and what we can do is that we can eliminate one variable and solve for the other. And what do I mean by eliminate? Well, if you notice, we have with x plus 1 and x plus 3, if I take the zeros of either one, we have one variable eliminated and the pathway to solving for the other variable to be created. And let's say if I solve for a first, so I'm going to eliminate b. So how do I get rid of b? Well, notice that b is multiplied by x plus 3. And if I set x plus 3 equal to 0, what is the x value going to be? It is going to be negative 3. Okay. And so if I take x and set to negative 3, okay, so I have 6, and I got 8 times the quantity. So with x at negative 3, so I have negative 3 plus 1, and I have plus b times the quantity of negative 3 plus 3. And guess what? So b is going to be zeroed out. So for what we have here, so you got 6, negative 3 plus 1 is negative 2, a times negative 2 is going to be negative 2a, and 6 divided by negative 2 is going to be negative 3, so a is equal to negative 3. So we'll have negative 3 over x plus 3. Now, if I go back to this equation, and I'm looking at eliminating a in order to solve for b. Okay, so with a, we have x plus 1 alongside the variable. And if I set x plus 1 to 0, we have the x is equal to negative 1. So we're going to have 6 is equal to a times the quantity of negative 1 plus 1. And we have plus b times the quantity of negative 1 plus 3. And again, so negative 1 plus 1 goes out. And negative 1 plus 3 is 2, so we have 6 is equal to 2 times b. And so we'll have that b is equal to 3. And so we have in the follow through, So in the follow through, so we have A determined as well as B. And so for 6 over x squared plus 4x plus 3, this is going to become negative 3 over x plus 3. And we have plus 3 over x plus 1. So those will be the partial fractions we have here. And if I were to add these together and combine it in terms of a single denominator, you would have 6 over x squared plus 4x plus 3. And just another case that we have regarding partial fractions. And for this one, okay, we'll say that we have 5x, we'll have 5x minus 2 over x squared minus 4 and so we have in the denominator, so we have a difference of squares. So we have 5x minus 2 all over, so we have x plus 2 times the quantity of x minus 2 and looking at forming partial fractions. Okay, so we'll say we have a is over x plus 2 and we have plus, we'll say we have b over x minus 2. Okay, and so just looking at taking what we have here, so just getting out of the fractions, multiplying the equation by both x plus 2 and x minus 2. And you don't have to literally write all this out, but if I multiply by both x plus 2 and x minus 2, okay, so we have modes of cancellation on the right hand side. And for what we have on the left, okay, both x plus 2 and x minus 2 go out. So left hand side, okay, we have 5x minus 2. And putting a and b in direct terms. Now we have for a, x plus 2 cancels, which we have the distribution of the variable over x minus 2. And as for b, okay, have a role reversal. Okay, so x minus 2 cancels, and b is going to be distributed over the other, what was the other denominator? Okay, so we have x plus 2. All right, so we got 5x minus 2, so you have a all over x minus 2 plus b all over x plus 2. And again, I can solve for a or b first, and we'll go with solving for a, so we can take out b. Okay, so looking at x plus 2, what makes x plus 2 0? It's going to be x is equal to negative 2. Okay, and notice plugging in for x. Okay, so what was the numerator? We have 5 times negative 2 minus 2. And we have is equal to 8 times the quantity of negative 2 minus 2. And we have plus b times, okay, the quantity of negative 2 plus 2. Okay, so b again is going to be zeroed out. To the left I have negative 10 minus 2 is equal to, and we have negative 2 minus 2 is negative 4 times a. So we have negative 12 is equal to negative 4a, and with division, okay, we have a to end up at 3. And as for the value of b, so I can eliminate the presence of a. If I set x minus 2 to 0, okay, where we will have the x is equal to 2. And for 5x minus 2, so we have 5 times 2 minus 2. And that is equal to a times the quantity of 2 minus 2. I have plus b times, okay, the quantity of 2 plus 2. So again, a goes out. 5 times 2 is 10 minus 2. For b, okay, we have 2 plus 2 is 4. And we have that 8 is equal to 4 times b, and we have a division by 4. So it is going to follow that b is equal to 2. Okay, so we have with the resulting partial fractions. Okay, so again, we're going to have a at 3. And b is going to be at 2. So for 5x minus 2 all over x squared minus 4, this will come out to 3 over x plus 2 plus 2 over x minus 2.